Hi, I'm Jonathan Mendelson, and today I'm talking about synthesizing Datalog programs. So let's say we have some relational data. We know which streets intersect each other, we know which streets have traffic or have green lights, and we also know where some crashes occurred. There might be some conclusion underlying all that data. And we might say something like a crash occurs between traffic on a pair of streets if the streets intersect each other, both have a green signal, and both have traffic. We can more precisely represent that conclusion using a logic program. Similarly, in networking, we might have some data captured from a network, and there might be some conclusion that we come to, again, that we can express in a logic program. And in a completely different domain, looking at program analysis, there might be some casts that we feel are unsafe or safe, and again, we can represent that conclusion in a logic program. So now we come to the central question of the talk. There's a lot of research on the evaluation of logic programs, but this isn't the focus of our talk. Rather, we focus on the synthesis of logic programs. Given input tuples and output tuples, what is the program that affects this change? Specifically, we focus on Datalog programs. Datalog is a widely used logic programming language that operates on relational databases. How can we synthesize Datalog programs? Doing so would allow us to quickly find complex patterns in relational data, as shown on the previous slides. So now I'll dive into the specifics of Datalog. A Datalog program is a collection of rules. Given input tuples and a Datalog program, the engine will create some output tuples. We'll use the program for an SCC as an example, the SCC being a strongly connected component in a directed graph. So for example, let's say we encode the edges of this graph as input tuples, and each pair of nodes that are in the same SCC as output tuples. So edge 1, 2 might be an input tuple because there's an edge from node 1 to 2. We can then apply rule 1 and synthesize the output relation path 1, 2. We can repeat this process using other input tuples or output tuples and applying rules to generate even more output tuples. In this case, we derive output tuple SCC 1, 3, telling us that node 1 and 3 are in the same strongly connected component. So again, we start with input tuples, we apply rules to derive output tuples, and we repeat this process until saturation. There are many previous approaches that have tackled the problem of Datalog program synthesis. And it's a challenging problem. Invented predicates are intermediate constructs for which there's no input or output data specified, which is a challenge because the synthesizer has to determine how to use these intermediate constructs or whether or not it needs them at all. Recursion is difficult because it can have unintended consequences. A simple recursive clause can create many tuples. So what's the specification? It seems on a surface level that it should just be input tuples and output tuples. But in the past, many approaches have also provided syntactic bias, or some sort of program grammar. These 4 commonly used tools all have different types of syntactic bias. So why is this a problem? The issue with these previous approaches that use syntactic bias is that they transform one difficult problem into another. The difficult problem of program synthesis into the difficult problem of defining the search space. And these approaches are extremely sensitive to the search space. With a search space that's too small, the desired program is likely not in the search space. And with the search space that's too large, the tool likely times out because runtime is heavily dependent on the size of search space. This is an example of what some of that syntactic bias might look like. So these are some candidate rules provided for ProSynth. Note that these are very difficult to manually write and difficult to automate as well. As a result, we end up with benchmark-specific tuning. Somebody wishing to synthesize something might have to already have some knowledge about what they want to synthesize or some knowledge about what a potential program might look like, which detracts from the usefulness of these approaches. So how do we define this problem? Notice our paper is called GenSynth, Synthesizing Datalog Programs Without Language Bias. Hence, we do away with the language bias and instead simply specify input-output examples. So how do we do this? Well, we solve both difficult problems at once. Notice the gen in GenSynth. This stands for genetic algorithm. So we use a genetic algorithm to define the search space as we synthesize the program. Initially, we start with a population of small valid programs. We determine the fitness using Souffle, one of the industry standard Datalog solvers, and we take the top few programs. Then we mutate these top programs and create a new generation. Notice that the search space is being guided semantically by the results of each generation rather than syntactically up front. This allows us to adapt to different problems and change the search space depending on what is needed. We continue this process until we reach a program that has a desired fitness and stop when such a program is reached. Now this is the accretion phase. Throughout the accretion phase, we improve the fitness of the program until we reach the desired fitness. But there is an unintended side effect, which is that we increase the program size throughout the phase. So we use another genetic algorithm to reduce the size of the program, the reduction phase. Now this time, the initial population is made up entirely of the program that has the desired fitness. Then we apply reductions which decrease the size of the program until we reach a program that can no longer be reduced. So throughout the reduction phase, we retain or improve the fitness, but the primary goal is that we decrease the program size. So ultimately, we end up with a program that reaches the desired fitness, but also is small and easily readable. So now I'll discuss the synthesis algorithm, and as I introduce concepts from the algorithm, I'll go into an example. We'll use SCC as an example and try to synthesize the program for a strongly connected component. We have a number of syntactic constraints that must hold true throughout the execution of GenSynth. Here's an example rule from the benchmark one object, one type. The first constraint is that we must respect the schema, meaning that if an argument appears in more than one relation, it must appear in columns that are of the same type. Each rule must be grounded, meaning that all arguments that appear in the head must also appear at least once in the body. And each rule must be connected. So if we represent each relation in a rule with a node and connect two nodes when they share an argument, then the head must be reachable from each node in the graph through a path. This is done because if there's a relation unconnected to the rest of the body, it won't affect the results of the rule, but it will significantly slow down the interpreter. So how do we create a seed program? Well, we want it to be small enough that it serves as a good starting point for the accretion phase, but we also want it to satisfy syntactic constraints. Seed programs are single clause by definition. So given an output relation and a schema, how can we satisfy the syntactic constraints using as few body literals as possible? We first must ground the two H arguments and one F argument in the head. We can greedily choose from the schema to choose input relations that ground as many arguments in the head as possible. In this case, the best we can do is grounding one at a time. So we ground each of the H's and the F. The benefit of this approach is that given a high entropy schema, we can quickly traverse a small space of clauses. There are only 38 valid seed programs for this schema, and we can quickly find one of them using this approach. However, with a low entropy schema, because we break ties arbitrarily, we still end up with a diverse population of seed programs. There are more details in the paper about how we enforce all the constraints and set the arguments in the clause, but I won't go into them in this talk. We'll start the example with a seed program. This is one of the two possible seed programs for this schema, the other one being SCC x, y if edge y, x. Notice that this program has a low F1 score because there are many false positives and false negatives, but that's okay, because this just serves as a starting point for the accretion phase. The accretions are the mutations applied during the accretion phase of the program. We want to choose as few accretions as possible to minimize bias, but we also want to be able to synthesize programs that are as expressive as possible. So where do we get inspiration for the accretions? The most straightforward accretions come from the idea that programs are built from clauses and literals, so it's natural to have accretions that add them. Append clause attaches a seed program to the end of the program, and append literal attaches a literal to the end of a clause. We want arguments to be mobile, so we introduce a swap mutation, which exchanges the position of two arguments. A common design pattern in Datalog are chains, where adjacent literals are attached by fresh arguments. This inspires the extend accretion, where we attach a new literal to the clause and chain it with an existing literal. Almost all previous approaches use prescriptive predicate invention, where the schema and existence of invented predicates are specified manually by the user. It is very difficult to determine whether or how an invented predicate should be used without specific knowledge of the task. This detracts significantly from the practicality of these approaches. We want GenSynth to automatically invent predicates. We don't want to have to specify the existence or the schema of invented predicates. This inspires the invent accretion, which doesn't modify the program semantically. Instead, it introduces invented predicate having the schema of an already existing literal. Finally, recursion is common in Datalog programs, but requires a base case and inductive step to be properly established. To increase the likelihood that this happens, we introduce the recurse accretion. The recurse accretion introduces a new invented predicate, establishes a base case, and establishes an inductive step. It's almost like an invent and extend accretion combined. So now let's see how the accretions function in action on the example. We start with the seed clause and immediately recurse on it to create two new clauses and an invented predicate. Note that this invented predicate represents a path, and since we swap on the first clause, exchanging the position of arguments x and y, this program now says that x and y are in the same strongly connected component if there's a path from y to x. So although this isn't the correct program for SCC, we've already discovered the concept of a path, and the F1 score has increased significantly. We now append a literal to the first clause, discovering that x and y are in the same SCC only if there's a path in both directions. However, in this generation, we also make a mistake. We use the append clause mutation to create the fourth clause, which says that x and y are in the same strongly connected component if there's an edge from x to y. This introduces a number of false positives. However, it's okay that we made a mistake, because GenSynth can remedy it using further mutations. We extend on the first clause, which doesn't semantically modify the program. Notice that we append a literal and swap on the fourth clause, which has been causing problems. Doing this makes it less likely that it is activated. As the clause increases in size, there are more and more conditions that must be met for the clause to produce any output tuples. Hence, we see that even attaching this SCC literal to the fourth clause increases the fitness up to 0.98. Finally, we swap, extend, and swap on the fourth clause, completely deactivating it. As a result, the fitness reaches 1.0, and we perfectly match the input-output example. We also append a clause to create the fifth clause, but this clause is redundant with the second clause, so it doesn't affect the fitness. Notice now that we have a program that matches the input-output example, but might overfit it and is difficult to read. This is where the reduction phase comes in. The reductions are mutations that are applied during the reduction phase. So what reductions make sense? Well, even when we don't semantically modify the program, we want to simplify syntax where possible. So we introduce equivalence-preserving reductions, which primarily aim to improve readability, such as remove repeating clauses, which removes duplicate clauses, and remove repeating literals, which removes duplicate literals within clauses. We also have a reduction called reduce invented predicate, which aims to remove invented predicates from the program. When we have a non-recursive invented predicate that is head of only one clause, it is often simpler to remove it altogether from the program without modifying the semantics of the program. We also would like to use reductions to remove unnecessary code, even if it means we modify the semantics of the program. So we introduce some semantic modifying reductions, which primarily aim to reduce overfitting. We have reductions called minimize clauses, literals, and arguments. Minimize clauses removes a full clause, minimize literals removes a literal, and minimize arguments sets two arguments equal to each other. If any of these reductions can be applied without decreasing the fitness, then it is worth simplifying the program. So let's see how the reduction phase works in practice on our example. Remember that we had an identical second and fifth clause. So we use remove repeating clauses on the second clause. This doesn't semantically modify the program, but it makes it more readable. Note that we still have the issue of the third clause, which we deactivated on this input-output example, but might cause problems on other graphs. So we use the minimize clauses to remove the third clause. We're able to do this because removing that entire clause has no effect on the fitness. Doing this makes it much less likely that our program overfits the input-output example. We use minimize arguments to set z and y equal in the first clause. And finally, minimize literals to remove the first literal from the first clause. Now no further reductions are possible, so this is the program that GenSynth returns. We've synthesized the exact intended solution, the smallest possible program for a strongly connected component. In the last few minutes, I'll turn to the experimental results. We evaluate GenSynth on 42 benchmarks from a variety of different domains. We have 13 recursive tasks and 12 tasks that require invented predicates, those intermediate constructs with no input or output data specified. We evaluate against ProSynth, which uses a constraint solver to prune the search space. and we compare on runtime and, importantly, on quality of result. For those familiar with Metagol or ILAS, we show in the paper that ProSynth is superior, so we use ProSynth as a representative in this talk. We'll start with runtime. So I'll just briefly explain this graph. In a second, I'll show some points on the graph. Each point represents a different benchmark. Any points that appear in the bottom triangle represent a benchmark on which GenSynth performed faster than ProSynth, and any points that appear above the triangle represent benchmarks where ProSynth was faster. So some takeaways. First of all, notice that GenSynth is faster on all 42 benchmarks. And also notice that ProSynth times out on 11 out of 42 benchmarks with a timeout of 1 hour, while GenSynth never times out. Now we revisit the motivating example, keeping quality of result in the back of our mind. Remember the program that we synthesized for SCC. It's compact thanks to the reduction phase. But when looking at a tool like ProSynth, which has no equivalent, its program is large and likely to overfit the input-output example. And in fact, we show that these two rules derive a path-output relation, in which case this last rule is incorrect. For example, on this graph, it says that 3 and 5 are in the same SCC because 1 and 3 are in the same SCC, and there's a path from 1 to 5. But 3 and 5 are clearly not in the same SCC because there's no path from 5 to 3. Hence, ProSynth has overfit its input-output example that it was trained on and was unable to generalize to this graph. We see this across all the benchmarks. We use program size to stand in for quality of result, as using an Occam's razor argument, a smaller program is less likely to overfit an input-output example. Again, any points that appear in the bottom triangle on the graph represent a benchmark on which GenSynth produced a smaller program than ProSynth. So some takeaways. GenSynth always produces a program smaller than 10 predicates on all the tasks, and GenSynth produces a smaller solution than ProSynth on all the tasks. One benefit of GenSynth is that it's able to handle noise. We compare with NTP because ProSynth can't handle noise. We'll compare on the benchmark countries because it's the most difficult benchmark from the NTP paper. It has 3 different levels with varying noise, S1, S2, and S3. So right away, notice that on S1 and S2, GenSynth is much faster than NTP and has a higher F1 score. On S2 in particular, GenSynth is 100 times faster than NTP. But we'll focus on S3. This is a solution synthesized by NTP, and these are the templates used by NTP. So notice how carefully the search space is guided by these templates. For example, in this rule, the same relation must be used twice. And in this rule, the arguments are actually specified in the templates. So the syntactic bias is not even allowing the synthesizer to decide the arguments that it will use in the program. Despite this, NTP has a reasonable F1 score. Now we'll compare with GenSynth. Notice here that GenSynth is free to choose its own arguments, so it's able to switch X and Z in the neighbor of relation. This allows it to achieve a much higher F1 score. So this is a perfect example of what happens when the search space is too small. Because the templates were hand-picked and so carefully crafted, a better solution was missed by the authors. So some limitations. GenSynth can't synthesize negation or aggregation, but that's likely achievable with additional mutations, and that might be the focus of some future work. GenSynth may be non-terminating. If a solution doesn't exist, GenSynth might keep trying to mutate and find a solution. GenSynth requires significant resources due to its parallelization. This is an advantage of GenSynth because it's able to run very quickly, but on the flip side, it requires a lot of resources. In conclusion, we introduce a new template-free genetic algorithm that synthesizes Datalog programs. The sample space is pruned dynamically over time using a genetic algorithm. We ensure accuracy using the accretion phase, while the reduction phase ensures that we have high-quality results. Our approach allows us to automatically synthesize invented predicates and gives us the ability to handle noise. And in the paper, we discuss more about the algorithm, more details on the experimental evaluation. We also have a discussion on avoiding local minima, so please check it out. Thank you.